People coming? Should we wait another 2 minutes? Maybe. Okay, let's wait 2 minutes. Okay, maybe we'll start. Okay, so hello everyone, welcome to today's class. So we will continue our discussion. Sorry? I saw okay, great. Wait. Hello everyone, welcome to today's class. So today we will continue our discussion of stable saddle points for non-convex optimization. So here is the plan. So let us recall what we did last time. So last time we showed that noisy gradient descent. In particular, if you add noise at every step, then this will escape saddle points. Yeah. There were a couple of issues here. So okay, I guess something that we did not do is so there was this high probability analysis which we did not do. Yeah, and there was some other. Okay, what we did not do this. We did not do going from quadratic approximation to function etc. Yes, we didn't do this. And one more thing we did do, which was this. Yeah, I'm sure how to combine everything. Yeah, okay. So we do these things. I will make a few comments about this now. So as far as the second point is concerned, today we will see this in more detail in another algorithm. So just kind of cover it. Yeah, and here about this I will not say much, but let me just say essentially why this is a reasonable thing. So the main comment was that your analysis of functional degrees is an expectation. So how do you combine this? Yeah, so how do you get a high probability bound for this? Yeah. And okay, I just said roughly speaking why this is reasonable thing. The point is that this analysis works for any starting point. And therefore, if I just take enough rounds, or let me call them phases. So if I just take enough phases, so that in each phase the function decreases in expectation, then with high probability over these phases, I will be able to get. Okay, so in each phase, f decreases in expectation. So high probability will decrease for at least one phase. Yeah, okay. Will decrease overall. Okay, I'm not saying it will decrease overall phases. Yeah, and essentially this is your concentration simply. And why is concentration possible here? Because this analysis works for any starting point. And hence you can treat these phases independently. So even though the phases might happen in sequence, but the random variables for the degrees are very different. So yeah, so that argument can be done in concentration. So, yeah, essentially that's the reason. Okay, yeah. And this thing, yeah, fit into also. I'm not sure if I want to cover it because this requires a lot of martingale argument, and you haven't written that yet. So this, yeah, not sure you will do this, but yeah, we will see later. But today I want to do something a bit more exciting. So I want to talk about faster algorithms for this. Yeah, so and what do you mean by faster? So it turns out that in the previous analysis, you need poly iterations. So yeah, quality of the iterations to converge. Yeah, essentially the stages are required. And why this? Okay, so first thing we did not do the proof completely, so therefore it's not completely obvious. Why? But let me just say roughly speaking why. Roughly because you are adding a lot of noise. Right, so in fact, in every single step you are adding noise. And also a lot of noise, right? We are adding a big amount of noise. We are adding like noise on the unit scale. Right. Yeah. So that's quite a bit of noise. And so because of all this noise, you have to reduce the learning rate quite a bit. And then supposed to keep learning rate one of the quality. And yeah, and obviously if you keep it relatively so small, then you will need a lot of iterations. Okay, so essentially this is crazy. And today, so we will see how to do this more cleverly. And in particular, we will see how to do this by adding very little class. So, kind of more clever procedures. So remember last time the hope was that if you just take random steps, yeah. So random noise at every step of enough energy of enough, the various will escape the circle. Yeah. So today we will not add so much noise. Today we will in fact add noise only very selectively and of low variance. We'll see exactly what this means. Okay, so here is the algorithm for today. So let's call it perturbed gradient descent to distinguish it from noisy gradient descent. So this is by Jin et al. 2017. And okay, so here is the algorithm. So for your iterations. So since this algorithm is actually quite complicated and long, I will do the analysis very only at a very high level. So I will leave out many constants and details. But here essentially the outline. So if no progress in a fixed number of steps using gradient descent, only then you add noise. Okay, so yeah, so it's a different algorithm. No? So now you don't add noise every time. You say, okay, only if I don't make progress, I'll add noise. And there's also not noise of unit radius, just of radius r, which is smaller. And otherwise, of course, you will, yeah. And the gradient descent step is as usual. That's clear. So xp plus 1 is xt. Okay. So yeah, that's a the algorithm. And what is R here? So roughly speaking, okay, so the important thing is R is roughly 1 over root t. Yeah, and remember last time it was 1. Okay, so this is a so you add much less noise now. And yeah, and this helps you keep your learning rate small because essentially you will jump around less. So you can jump around less, so you can have a large learning rate. So allows for large learning rate. And how large? In fact, it will turn out to be a nice learning rate. So yeah, so even in the best case, you cannot ask for learning rate more than 1 over L, right? If it's L smooth. So in fact, you can make it as far as that. Yeah, so but that's the big change now. Yeah. Okay, so yeah, so I will not say exactly how many steps this is. So this is the number here, and also you need to say what no progress is. It's going to be zero progress. There has to be like a cutoff. So yeah, these are some numbers. So there's some number here, and I don't want to talk too much detail about. Yeah, but yeah, but this right here is the main change. Okay, great. So okay, now I'm seeing how to analyze this. Okay, so here is the outline. Okay, so suppose I am stuck at a starter point. So here, it's some x0. It's x0 is your starter point. And now let's say you yeah. So you basically you fail to make progress, and what does that really mean? It means that okay. So in our algorithm, we suppose we fail to make progress. So then it should mean, and this is I think intuitive also, that you must be near a certain point. So you must be stuck in a small region. Right, because if you were not stuck, if you were moving a lot, then likely you would have made progress also. Yeah, so it is kind of intuitive. We'll make it precise. Yeah, how small and what stuff means. Okay, so this is kind of believable. Okay. Then the second point is that suppose you are stuck in a small region. Then yeah, so maybe it's a small region at some point x tilde. Then suppose you take 2 points near x tilde. So yeah, so I'll quantify later what near means. So yeah, there's a precise meaning to near. And what are these 2 points? Let's say you have a point x0 and another point is x0 plus r0 e1. Okay. So what's going on? So let's draw a picture. So let's say this is your and yeah, and somewhere that around here you are struggling to escape. Now let's take 2 points. One is x0. The other is x0 plus this eigenvector. So this is r0 times you move r0 in the distance e1 in the r0 distance in the direction e1. And what is e1? E1 is what you expect it is. So E1 is your put direction. E1 is the direction of most negative eigenvalue of STL. at x0. Actually, no, let me call it, make it x tilde just to be more precise. Okay. So, okay, so if I take these 2 points, then I must be able to escape from at least one. Then gradient descent will make progress. From at least one of these things. Okay. Okay, so let's make that a kind of a friendly technical statement. So what I'm trying to say? So I'm trying to say that look, if I can make progress, then we're very stuck in a small region. And I want to say that this small region is actually very small. So our goal here is to bound the volume of the small region. Why is this a good thing to do? Because recall that we make this random perturbation. So this volume is very small. The random perturbation will be able to escape this hypothesis. So you want random perturbation to escape. So to be more precise, let me draw a picture. So here is so let's say here is your all possible random perturbations. So here is maybe your current point, and here is all possible random perturbations. Okay, so the radius of this sphere is r. And now, what are we saying? So I want that the region for which I will pay to escape is smaller. So maybe, so hopefully my region looks like this. So this is the bad region. So this is a region. So there, if my perturbation goes here, so if my random perturbation is in this region, then I will get this. So then I will get yeah. Whereas here I will. And yeah, so if I can suppose though that this region where there to escape is really like this, it's very thin region of a very small volume. Then with high probability I will be able to escape. Right, because remember my prediction is random, right? So sample random prediction. So yeah, so if a region is so thin, so essentially all I have is this thin disk here. Then I will yeah, then I will not line this sentence with the problem. We need to be ready to show this is bad. And what direction is this? This direction is what is expected. This direction from the previous condition. This direction is the even direction, or even, yeah. So this is the even direction. Okay. Does that make sense? So yeah, so again, let's look at this line again. So essentially, I'm trying to show that my bad region, where I just struggle to escape, will actually look like this. So what does it mean to say that my region looks like this? So let's try to understand this more materially again. Look at this. Let's pull it up. And give me some point. X0. Give me any point X0, which is near this. So let's say my X0 is here. So then if I make a move in this direction, then if X0 happened to be bad, so if X0 was bad, then X0 plus RE1 cannot be bad. So this R0 even cannot. So what this means is that the thickness of my region in the y direction cannot be much. The thickness along even direction can be only R0. So the problem is that since this function could be very complicated, I cannot really say exactly what this shape is. It's here I just not simplified this here, but it may not actually be a disk. It can be like whatever weird relation. It can like go up, down, all that stuff. Yeah, it can like be really weird. Yeah. But what he's saying is that give me any points inside this pad area, then that point plus R0 even cannot lie if I divide it. So yeah, so I have no idea what the shape of this pad area is where I cannot escape. But what I can say for sure that at any point thickness cannot be more than R. And yeah, so and R0 is like very small, then it means that relative to my whole ball of partitions, I should do very well. So the band region must have very small. So yeah, so that's what we story. Okay, we'll take a minute to adjust this.
So so like after you add the noise, the resulting point would be over some sphere around this X naught.
Yeah, exactly.
So like so here you said like either X. So this X naught you mean in the interior of the sphere?
No, okay. So okay, so I think this picture is again bad. So what I am drawing is yeah, okay, really bad drawing. So this bad region, this red region is on the surface only, okay. So we should not draw this surface. This is so oh no, okay, okay. I think I will know. Oh no, okay. Yeah, no, I think I got it. I got confused. Yeah. No, I think it was fine. So okay, so I think the maybe what was unclear about the noises. Okay, I think maybe that's where I was confused. Yeah. Okay. So this is in the ball.
Yeah, just a point on the ball.
Yeah. So this could be effect ball. This is not the sphere. This is not the surface of the sphere.
Not S0.
Yeah.
So this is like some uniform distribution
Over
over the ball.
Yeah, exactly. Yeah, good question. Yeah, this is different. Last time we had S here represents. Okay, cool. So, yeah, everything is fine. Okay, cool. Okay, so I guess the big picture like around try to make things sense. Okay, so I will write here 3 lemmas. These are all a bit approximate lemmas, but it's not precise, as precise as possible. Okay, so if f of xt minus f of x0 is bigger than minus let's call it c, then for all t most t xt minus 0 is most 0 to eta xc. Okay, so what am I saying? I'm saying something very simple, that if a function fails to decrease for many steps of a process, so if it fails to decrease by even c, that was happy the case that I was stuck near my initial point.
Is Polaris C or some C?
So this look of my is yeah, well, let me see. Okay, so this is lemma 1. Then lemma 2 says consider x tilde such that the minimum eigenvalue of the Hessian is small. Okay, so here I will use a slightly different scaling. So here I will say this is at most minus square root rho epsilon. And this is in fact the standard scaling we use in X. Yeah, so and here rho is the reflectance of your Hessian. So your F is rho Hessian Lipschitz. So this is like a proxy for your state shadow condition. So now I'm just putting my amount of state shadow in terms of this rho now. So yes, suppose we have this, and x0 prime, which is x0 plus non-zero even, or at most are away. So they're both within the fall. Where even is the most negative eigenvector of Hessian. Then for yeah, sufficiently large T, and small and sufficiently small r, and C I'm not sure why. I think it's probably not negative. I'll remove this for simplicity. Yeah. So, yeah, so let's try to understand the point here. So, again, let's say I'm at some external. I think I'm at some starting point. Like in the previous analysis. And it's also like intently strict. So, your minimum packet value is quite negative. At most minus -0. And now give me these 2 points. So, take your external. Inside my ball, I had 2 points, x0 and x0 prime. So they're both at most r away. And again, x0 prime is x0 plus this r0 even. Then for sufficiently large, yeah, t for enough depth, you will not say exactly how many, and if r is small, then you will have that either you'll gradient descent starting from x0 to this state, or from x prime 0 to state. So look at whichever decrease more. At least one of them will decrease by n set of c. So again, I'm adding like many constants here, but this is roughly the you try to. Okay, cool. Okay, so let's try to prove these things and then it become a bit more clear what's hidden.
So that is the mean of so x3 prime is the gradient descent starting from x0 prime.
Yeah.
And So they're like student
Yeah, this should be.
Yeah,
The second term should be x f of x minus f
f of
of
x.
nine.
Oh, that's this should be, yeah. This should be a good line, right? Yeah.
So like it is like after, so every time after doing some capital T iterations, which you were choosing in a certain way, you were checking whether you were at a saddle point or not. And then,
So, okay, so yeah, so let's go back to our thing. Yeah. So all I'm saying is that if you don't make progress, and a lot of that, then you do a partition. So what the previous lemma is telling you is that this will not happen too many times. Because there's a good chance that you will give a twist. So sure, so it's possible that maybe it's a bad direction and then you again don't make progress. But after enough epochs of not making progress, you will eventually get a good question. That's yeah, so I'm not explicitly checking if I'm at a standard point. But yeah, but this partition essentially is
yeah, that you were checking by just taking the
comparing the function value.
the function value.
Exactly. Okay. So let's try to do this now. And I guess it will become more clear, but all was not said.
So and also this noise also you were adding like after this capital T iterations of breaking this and then checking whether you are in progress.
Yeah. So
Okay.
we go back here. I think put in a 60 differences from the previous diagram.
Yeah.
So this only happens if you don't make progress.
Yeah.
Otherwise, it just breaks.
So like unlike noisy gradient descent, you are only adding noise
Yes.
to fewer times.
Exactly.
So you have like a set number of epochs, and at the end of every epoch, you check whether you made progress or not.
Yeah.
If you didn't make enough progress, you add noise. If you made enough progress, you then go to
Then
the
yes. All right. Okay. So first, let's prove the easier lemma. Lemma one. So let's give them names. Let's call this. Yeah, let's call it the entrapment lemma. That if you don't decrease, then you will be entrapped. Then you must have been trapped. And yeah, and let's call it escape lemma. That you must escape from at least. Okay, so let's prove this entrapment lemma first. So it's actually really easy. It's like a warm up. So let's look at our distance. So xt minus x0. So remember, I want to show that my point xt is close to x0 if my function value did not decrease. So I have to upper bound this distance. Okay. And so let's think about how I got to xt. I got to it after some iterations, right? So let's see what happened. So I did some t iterations. In every iteration, I moved from some xr minus 1 to some xr. Okay, sorry, I think, yeah, type it outside. This is what I did. Okay. And now this quantity is at most square root t Yeah, exactly. Yeah. Yeah, so this is called the shorts. And then why? So this is because of my gradient descent. Okay, yeah, I'll just write this in more detail. So yeah, so you can show, I think, as you've seen like many times before. So if you do one step of gradient descent, that ensures that f of xt plus 1 minus f of xt, your degrees, is always at, yeah, so if you always decrease by quadruple, always decrease by this much, provided your learning rate is smaller than 1 over smoothness. And yeah, and now you can say by smoothness again that this is as you don't know smoothness, this is even easier. This is literally just gradient descent. The same as, yeah, this is gradient descent. This is the definition of the gradient descent. Yeah, so this you know. Okay, so there's nothing very deep here. Yeah, and this is essentially what you wanted, right? So this degree here is your C. Okay, yeah, so don't worry about this, is not very deep. Okay, okay, so now this is the good part. The second lemma. Is the escape lemma. Okay. Okay, so what we will show that okay, okay, so if if the lemma fails, okay, so basically prove the contradiction. So if it is not true that they both escape, so yeah, so if it is not true that at least one escapes, then yeah, then the both of them are stuck, right? Yeah, yeah, so okay, so if it's ever fails and yeah, then something goes wrong. Okay, we'll see what goes wrong. So in fact, it'll turn out that your xt and xt prime are far away. So this distance must be large. Yeah, so this is what we will show. Yeah. And why will this be contradiction? Because we made something in me. So if this distance is very large, then why is this a contradiction?
You can both be stuck.
Yeah, exactly. They can't both be stuck. Yeah, this is a contradiction, as both can't be plugged near starting point. Exactly. Yeah. So this is what we will show. So, okay, great. So let's review that lemma fails. So lemma fails, and hence, yeah, we are using the entrapment lemma. Xt minus x tilde yeah, is at most xt minus x0 plus x0 minus x0. This is not entrapment, this is triangle inequality. So using entrapment lemma, if the lemma fails, then this must be small. Then this is at most square root 2 eta tc. And this is value at most r. And the same thing also true for the other guy. And so explanatory. Yeah, both by the same reasoning. Okay. So we'll just give this a name. Let's call this D, capital D. Okay. So also denote by H the Hessian textile. And now remember, I want to show that xt and x prime t are. So and that's why what I will do is I will track the distance of the two trace meter. So that's the idea. Idea is xt minus xt prime. What tracks now? This is let's do that. So yeah, let's call W2 this difference. WT is xt minus xt prime. Okay, and well, what are these things? These are just gradient descent iterates, right? So let's try to compare WT plus 1 with xt plus with WT. So WT plus 1 minus WT. Okay, who will tell me what this is?
Beta times gradient xt minus gradient xt prime.
Yeah. Oh, sorry. Writing is a bit Good. Yeah, okay. Yeah, exactly what you said. Okay. And now I want to use the fact that my function is lifted in the Hessian. And using that, I can say that this is minus eta h xt minus xt prime. So what am I saying? So a plus and error term. Yeah, so see, Hessian is essentially just the second derivative, right? And grade is the first derivative. So saying that the difference of the two gradients is the derivative of the gradient, the Hessian, applied on your xt minus xt prime. This is essentially your Taylor's theorem, definition of what Hessian is. And but then there is some error because the function is not quadratic. So yeah, you have some higher order terms. And what is the error? Well, you can write the error as minus eta some delta t wt. Okay, so but this is wt. So this thing here is yeah. So and there's the error. So how much error will you suffer? So just like for first derivative, you can see how much your Hessian has changed over your movement from xt to xt prime. So you say, okay, let me move from xt to xt prime. Let me do this computation. So t to okay, so what is it saying? It's saying that if you look at the path from xt to xt prime, and if I define a one-dimensional function along this path, so theta here captures my 1D function along this path. Now, what is the 1D function? The 1D function is this thing. So this function xt prime and xt are fixed. It is only variable. It's here taken from 0 to 1. As I move from xt to xt prime, theta very given, and this captured how much my antenna is taken. Yeah, and that's actually the correction.
Minus h that h of w.
So h I was Hessian in the beginning. Okay? So h. Sorry, what's your question again?
Yeah, what is that h on that what that h is calculated?
Oh, okay. Yeah. So this is right. This is at x delta.
Okay.
Yeah. So essentially, I'm trying to pretend in the first term that my Hessian every grade is h. And this capturing how much mistake I've made by doing that.
Yeah, that's okay.
If every grade this would have been clear, but not every grade. So I suffer some error. This is how much it is. Okay, great. So yeah, and now you can expand this out. So this is now a recurrence in WT. So this is, you can expand this out and you'll get touch +1 W0 minus eta T. Yeah, so I haven't done anything here. I just find this out. And this kind of makes sense because so for the first term, essentially, I'm doing an differentiation at every time. So okay, so by the way, this WT goes here, and that's why you get this height. So place the WT here. Maybe we get this right, like this. So WT plus. That's fine. It's WT. Okay, this. Right more. Yeah, read like this. Like now out like this. Yeah, so the thing is the power up. But here I get a different delta t each time. So they get raised to different powers. So the first delta t will be raised to the entire power, I minus theta h to the t. The next one will be raised to one power less. So yeah, that's all. Okay. And in fact, here you use the fact that the Hessian is roll shifts. So the norm of the delta t is at most rho times max of xt minus x tilde xt prime minus x tilde. Remember the Hessian was calculated at x tilde. So I'm trying to figure out what the norm of this thing is. And since the Hessian only changes by rho over this distance, delta t is norm can be at most this. And it is at most my rho times my d. Great. Okay, and then using some calculation, you can show, you can show that this term here is not that large. This can be shown to be at most half the first. Okay, so yeah, I'll attach the calculation later in the on the web page. Like, but yeah, this is kind of boring. I don't want to do that. But I just like a final abstract of everything. So the upshot of calculating all this is that your WT, so your difference between your two GD iterates at step capital T, this is at least I minus eta h to the capital T W0 by 2. Yeah. So this is the pipeline. And now here we use the fact that our HPN is not
So W0 is in the direction.
that is interaction as I so I do that. So remember W0 was R1 R0 even. Okay.
F1 is an eigenvector, so
So this is at least 1 plus eta square root rho epsilon. Remember, rho epsilon square root captured my curvature of the function in the most negative direction. So so this says that my 2 points will become very far. Okay. And then we can give us a linear from here. Sure. 2 points are very far. So if they're both very far, then if they're very far, then they cannot be both interact. That's one reason. So for at least 1 point, you must have networks. At least 1, 2, must. So this is a clear story. For the exact equation of how to do this, that's a really paper answer. Nice. Okay, so this was cool. And now let's do this is the most fun part left, which is of how to figure out the volume of this region. So I think I drew this rough picture that look if this is your external. So if both x0, so if x0 is in the bad region, then x0 plus r1 cannot plus r01 cannot be in the bad region. Plus r0 cannot be bad. So this was a picture which I had drawn. Okay, so from here I have to kind of do this argument that the volume of bad case can't be reached. So let's do that. So again, I will kind of do it sloppily, not do all the details. So this is the last lemma, which is the volume lemma. So I just state it again imprecisely. So consider extruder such that gradient of that extruder of epsilon and lambda min So this is essentially like a saddle point. Okay. Then define x duct to be x0 such that x0 is in the ball of radius r. Remember that's your perturbation ball. And f of xt minus f of x0 is this. So you have failed to make progress. So this is really your bad stuff. Okay. And the lemma says then volume of x duct is at most delta times volume of of the ball. Okay, so this is essentially what you want to say. Yeah, again, I'm not saying exactly what delta is. Too long to say. But let me just say essentially why this will happen. I mean, one day but I wanted to degree along. My much smaller than this. And so this is the idea of the okay, so let's set this exit R0 to be delta R square root 2 pi over T. So, okay, so now we know from previous lemma, from the escape lemma, that X struct has width at most R0 in the minimum eigenvector direction of H. Okay. And yeah, and this implies the volume of the struct region is at most R0 times volume of the ball of d minus 1 dimensions of radius r. So why is that?
Here you are assuming that your X is like convex or something. You don't have like multiple bands of region.
No, this doesn't assume convexity. So the
Or maybe one, so like you could have like multiple bands of width R0, which are R0 distance apart, and they could all be extra.
yeah, so I think this requires more careful.
Not just for exactly R0, but for any distance beyond more than R0, you should your scale dimension for it, then it could work.
Oh no, okay. So I think, yeah, of course. I think the previous setup we got is that user that X0 plus R R0 you can explain, but even anything beyond it also.
So
So,
anything, any distance beyond R0,
yeah.
2 points are any at least R0 distance apart, then one at least one. Then you can only have band.
Yeah, exactly. So a little bit more carefully than indeed. Okay, yeah, so this is really the punchline. Okay. And now you use the fact that these balls of higher dimension, their volume will decrease quite fast. So in particular, you can use this classical result. The volume of the ball of radius d of radius r in dimension d is r root pi gamma d over 2. It's fine. Yeah. Okay, yeah. So
D.
sorry.
R to the power D.
Oh yeah, okay. True. Root party. Yeah, that's the party. Yeah, and somehow yeah, and this is increasing really fast. Yeah. Yeah, and then this must be much smaller. The volume. Yeah, so that's roughly the point. It's okay, yeah. They have to skip some details here, but hopefully this clarifies the main picture of why all this should work. Yeah, so it's not in a book, so yeah, this was a paper. So this is whatever I could extract it out from, without having too much detail. And but yeah, for more details, the paper actually well written. So it's quite long, it's like some 30 pages, but yeah, it's quite well written. If I would have the paper also on the page. Okay, great.